Okay, well, hope you guys all had a good Thanksgiving. Mine was too short, as usual, and I gained too much weight, as usual. So maybe we can all diet together or whatever. Anyway, now, it was a long time ago, but at the end of class last time, what we did in lecture last time is we introduced this concept of a general n-way tree, like we have on this figure. And remember, the difference between an n-way tree and a binary tree is that you can have more than one data value in a node. All right, and then we had these little lines with the circles that represented the empty tree, and so we said that this is a figure, an abbreviated rendering of an n-way tree, right? And then we looked at we looked at what a vector is. We reviewed what a vector is, because in the implementation of an n-way tree, in this figure, we have the code for the attributes of an n-way tree, and we have these two attributes, underscore data and underscore children. And what is underscore data? It is a what to a what? A pointer to a vector. So here on the board here, we have an example of a node. This node has 1, 2, 3, 4, has size 5, indexed from 0 to 4, and underscore data sub 0 is 50, underscore data sub 1 is the 20, and underscore data sub 2 is the 90, and so on, right? And then the children, underscore children is a what? It's a pointer to a vector of what? Pointers to n-way trees. Are you with me? So this line down here represents underscore children sub 0, and it is a pointer to another node that looks like, it is a pointer to a tree, which is this. It is a pointer to a tree. So this is the composite pattern. Remember that? Does everybody familiar? Remember how we did, how this worked? This is an example of an n-way tree, and the two attributes are underscore data and underscore children. And underscore children is a, now what is it again? It's a pointer to a vector of pointers to NTrees. So this is a pointer to an n-tree, this is a pointer to an n-tree, this is a pointer to an n-tree, and this whole thing is an n-tree. So it's the composite pattern. And you remember, now here's the thing, we're going to have to understand that these are vectors, and so we're going to have to understand, remember how vector operations work, because whenever we do the operations on an n-way tree, whenever we implement them, we're going to have to remember that what we're dealing with are these vectors. And remember what we can do with a vector? We can append, we can insert, and when you insert, what does it do? It shifts everything over and sticks it in. Remember that? And the other thing that we wanted to note, that we note here, is that there's always how many children compared to how many data? One more. Yeah, there's always one more child than there is data. So we've got to remember that. We looked at the definitions of three basic operations. This one is NTree splice at, and so we saw the way to grow a tree was to splice another tree into it, splice at. And then this next one was split up at, where we took a data value and we split it up. And this third one was split down at, so we had a tree and we take a thing and we split it down, and then the two ones that are left get joined as the single root. And then what we did is we demoed, and this is going to be the visitor pattern. And then what we did is we demoed those three operations. So if you're not clear on, if you don't remember that, it's all on the video. So I finally got that posted. So anyway, it's on NTree, the demo. So we need to remember that. Now what we're going to do today is we are going to see how to implement an n-way tree. Okay, and some of the code here is going to be left for you to do, okay, as your next programming project. And so the project is NTree. All right, so here we go. Now, so we're going to do a bunch of code walkthroughs to see how all of this stuff works and give you some hints on how to do the homework. Okay, so first of all, let's take a look at, we had a couple of private constructors and we had a couple of public constructors. Now this is can we tell here from this code? What are the parameters here for this constructor? This is a constructor for an NTree, right? And how many parameters does it have? 3. Left, val, and right. Are you with me? It's got left, val, and right. And we looked at the preconditions last time. We assumed that left and right have already been allocated. They already exist. So we're not going to do anything, allocations here with the new operator. And look what it does. The way it works is it does data arrow append val underscore children arrow append left underscore children arrow append right. Now how in the world does that do what it's supposed to do? So look. In the beginning, we assume that we have 2 trees that have already been allocated. There's my tree in this example. There's my tree with data 60 and 80, so 2 data fields and 3 children. And those, oh, and by the way, that's our symbol for the empty tree, right? The little circle, the line with the circle. So my tree, 60, 80 with, and then your tree was 70, okay? And now here's what the way this constructor would work. You would say NTree, my tree, comma 30, comma your tree. So you see my tree would correspond to what? What's the parameter? What parameter? My tree is the actual parameter. The formal parameter in the constructor would be what? Left. And then 30 corresponds to val, and then your tree corresponds to right. Are you with me? Is everybody clear? So now look how this thing works. How does this work? It does underscore data dot append val. Now what's with this append? Because underscore data is what kind of a, what is it? It is it's a vector. And one of the things, and so underscore data gets initialized to be the empty vector. So do you understand that append, what does append do? That, for a vector, what's the vector operation for append? It puts it at the end, right? But if it starts off to be empty, it puts it at the end. Are you with me? So see, so what that does is that appends the 30 here. And then what's this underscore children arrow append left? What does that do? You see how it's working? It appends this to this. See, look, it starts off like this. It starts off underscore data, empty, and it starts off underscore children, empty. So it appends data. So now if it appends data, then there's the 30. See, it gets appended to that. And then what does it do? It appends left to children, so that puts this one, and then it appends this one to this one. But it's appending it because that's a vector. You see how that, does everybody see how that works? These are vectors, and so the way this constructor works is by appending. Yeah?
So after the colon, or...
Yeah, okay, you're talking about this colon?
Yeah, is that the initializer list? So,
yes.
So good. That is the part that pre-allocates the children.
Oh, I wish I had said that. That was good. Thanks for clarifying that. Yeah, that is the, yeah, I should have pointed that out. That colon starts the initializer list, and that's where we get the new vector. Underscore children is new, empty one, underscore data is the new empty one. And when those get initialized to the empty one. Yeah, I should have pointed that out.
Is the children and the data connected when there's no values in it? Or is it just like... We assume here the precondition is that my tree and your tree have already been allocated and pre-exist. That is a precondition. I don't know if that answered your question. No, like what I'm just, it's like there's data like this, like, yeah.
That's when it creates this to be an empty,
right.
Empty, and creates this to be empty.
Oh, okay, so they're both empty. Okay.
Yeah, and when it creates them, it creates this to be empty, it creates this to be empty, and then it appends the data, and then it appends this, and then it appends this. Because they are vectors.
Right. So what I'm asking before, does the appends, like when everything's just like initialized, like
to the empty, yeah.
Yeah. Is there any connection between the data and the children, or is it
no
specific append that does that?
Yes.
Okay.
Yeah. Mm-hmm.
Well, even after the append has happened, the data and the children is not connected?
Well, yes, they are, because look, let's go back to here. Because they are connected as being attributes of this graph.
But in
Do you
terms
see what I'm saying?
these lines that are drawn, technically, it's not as if child 0 is connected to data 0, which is connected to child 1.
Well, you're right.
In that way, it's like this is a vector.
Actually, yeah, these are separate, right. These are, I think the answer to your question is no, they're not connected physically, but on the other hand, they are, each one of them is separately an attribute of the same graph.
Right.
So that's the way they are connected. I mean, that's why we draw it like this.
But essentially the children are a vector of themselves, each connected to each other. Not connected, but like as a vector, they're together.
As a vector, it is sub 0, sub 1, sub 2, like an array. A vector is an expandable array. And so, yeah. Are we good? All right, these are all good questions. Yeah, question?
On the next slide.
It does underscore children new, and it does underscore data new. So when it does those new, when it does those new, that's when these get, that's when this gets allocated with a new, as a new one, and then that's when this gets allocated as a new one. And then in the body of the constructor, the 30 gets appended, then this gets appended, then this gets appended. And the reason it gets appended is because these are vectors, and you append it, going this way. I tell you, to understand the way this constructor works is crucial to understanding how the code's going to work from now on when we do this implementation. So these are good questions. Yeah.
Is there a way to make it so you have like multiple datas and multiple children?
Well, in this constructor, no. No. In fact, we will, actually, here's a constructor where if you have pre-existing vectors of children and a pre-existing vector of data, you can construct it with those. So, anyway. Actually, that was a good question for the next slide. Now, we also have two public constructors, and these construct, instead of having pre-existing trees, these construct trees from scratch. All right? So, here's a constructor. This constructor has, how many parameters does this constructor have in its parameter list? Trick question.
What?
How many parameters does this constructor? None. So this is a constructor with no parameters. And what does it do? It does children new vector p underscore data new vector p. So if you call NTree, you just get the empty tree. Mm. Now notice that the empty tree actually has two vectors in it, and each one of them has size 0, but if you go back and look at our vector implementation, it actually has capacity 1. So I mean, there is something there on the heap for the empty tree. You see what I'm saying? Something from the heap is there. And here's another constructor. With this constructor, how many parameters does this constructor have? 1. And what is its type? T. Constant reference T. Okay? And so if we say, here on the figure below it says, if we say NTree 30, it creates a tree like this. 30 with, does everybody see? Okay? And so how does it work? It does, well, we get new underscore children new underscore data new, and then data arrow what? Append val, and then children arrow, now children arrow append what? New empty tree, and then children arrow append another new empty tree, so that puts those there. Empty trees there. Yeah? Are we good? Okay. And then we have these getters. This is the implementation of the getter. Now let's see how this code works, because what is the type that get data returns? All right, so now what is the type that get data returns again? Type T. Now, do you see? Oh, and by the way, you give it the index from which you want to return. For example, if we said get data, if we said get data parentheses 2, what would get returned here? 90. Now, do you see how that works? Because what is underscore data? It is a what to a what? It's a pointer to a vector. Yeah, to the underscore data. So star data is a vector, and then that vector sub I is the ith element of that vector. Yeah. No, that's a good question. The question is, why is it star underscore data? The reason is because, let's always go back. Let's always go back to the NTree implementation. Look, what is underscore data? It is a what to a what? It's a pointer to a vector. That means star underscore data is a vector. It's what it points to. Are you with me? And so it's that vector sub whatever. Now that was a good question. Does everybody see how the syntax works here? Okay. And then same way with children. It's star underscore children sub I. Are you with me? Is everybody clear? Okay, good. Now let's implement those three operations. What do you say? Okay. Now the first one is splice. Splice at. So this is the NTree, this is our n-way tree splice at operation. Now, so here I have a sequence of snapshots, execution snapshots, and what we're going to do is we're going to trace through the call to mytree.spliceat parentheses 2 comma your tree. Now before we actually go through the details, can we imagine what's going to happen? In part A of the figure, we have my tree on the left and your tree is on the right. And do you remember how the splice at worked? Remember what it did? It took one of the, remember when we demoed it last time? It took the receiver tree and what did it do? It ripped it apart and spliced your tree at that position. Remember that? We demoed that? Okay. So can you visualize what's going to happen before we go on? Can you visualize what's going to happen if we say my tree.spliceat to your tree? Well, where is my tree sub 2?
40.
Yeah, well, yeah, 0 and 1 and 2. Yeah, 30 is sub 0, 90 is sub 1, 40 is sub 2. Right? So where's it going to pull it apart? It's going to pull apart my tree between what and what? Well, yeah, it's not between 40 and 60, it's between 90 and 40. Are you with me? Now imagine, before we go on, imagine you pull apart my tree between 90 and 40, and you take your tree and you stick it in there. Now can you see a problem with the children? Before we go on, let's imagine. Imagine you split the 30 and the 90, and you keep that on the left, and you split 40 and the 60. You pull it over here, and you want to put your tree, you want to put the 70, 80, and the 50 in between the 90 and the 40. Can you see an issue with the children?
Too many.
Say it again?
There's too many.
There's too many. Are you with me? Because there's always what? There's always what? One more what? One more child than what? Than data. But here, we'll have what? Altogether we'll have what? 1, 2, 3, 4, 5, 7 data. So we should have what? 8 children. But how many children do we have?
8.
I think it's 9, right? 1, 2, 3, 4, 5, 6, 7, 8, 9. It's 9. Is everybody clear? Does everybody understand the issue? The issue is that we have one more child. Well, there's going to be some child left over. So guess which one is going to be the leftover orphan? Can you guess? When we split the 30 and the 39 and the 40, 60, can you guess who's going to be the orphan? I mean, it's hard to tell ahead of time, but I mean, because it's one of two logical ones.
Is it I?
Well, I would still be, oh, yeah, it could be I. Or it could be C. It turns out it's going to be C. Yeah, it's hard to know ahead of time because it's just the definition, how this operation is defined. C is going to be the one that's left over. So let's just remember that as we go through this. Are you with me? The child C, ABC, the one between 90 and 40. Because what's going to happen is we want all the children of 70, 80, and 50 to be spliced in there. But that's not. But then C is going to be left over. Do you see? All right. So anyway, this is our initial tree. So here are the steps. In step B, what we do is we remove I from your tree, and we replace the right child of 90 in my tree with it. Now, do you remember how we, yeah, so anyway, and here's the picture. So you notice that where did we put I? We put I where? As the what? Right child of 90. And so C is still just hanging out there. Do you see what I mean? Are you with me? And where did that I come from? It came from what? For the right child of 50. Now, why did we do that? Because it seems like it's got to be to the right child of 50 still. Well, because now here's what we do. Oops. Now here's what we do. In a loop. So can you imagine? So now we're going to do things a pair at a time. In other words, the data and the child. A pair at a time. So in this step, we remove 50 and H from your tree. Now, do you see the 50 and the H? It's 50 and its left child. And what do we do with that 50 and this left child? What do we do with the 50 and the H? We put it where? We put it in here. But now we can do that using what? Insert. With a vector. Are you with me? So that this pair, this 50 and the H, goes right in here, and so boom, and so everything moves over, because that's how vectors work, right? And then what? Tell me what's next. We take the what? We took the 50 and the H, now what do we take? We take the 80 and the G. And by the way, how do we take the 80 and where do we take the 80 and the G from? I mean, how do we do that? We just, yeah, well, we'll show you the code here in a minute. And so this 80 and the G, so the 80 and G, so they go in here, and so this moves over. And now what? Then what? Next pair, what? 70F. The 70F. Go here, boom, and there we have it. Insert them between, and now what happens is, this tree has become the what? The empty tree, and this C is left over. Now it's the responsibility of the caller to deal with that. In other words, we don't deal with that. The splice at does not deal with this C. Whoever calls splice at has to do with the caller whatever that the caller wants to do with it. So that's the responsibility of the caller. All right? Now, so here's a little summary. The caller of splice is responsible for the leftover child pointer. There are two special, and also there's two special cases. There's a case where the receiver tree is empty, in which case there is no leftover child pointer. Now remember, okay, so if the receiver tree is empty, then there's, then it's just, you get spliced into the empty tree, there's no children left over. And then if the tree spliced into the receiver is empty, then splice does nothing, and so there's also no leftover child pointer. So the caller of splice has to know that and has to handle any leftover child pointer if it needs to. And now let's do we'll do a code walkthrough of splice at, and notice down here at the bottom we have what? Exercise for the student. Okay, so now let's see if we can understand how this code works. Okay, so void NTree splice at I NTree star tree. Okay, and here I've implemented the precondition for you. Okay, this is just, can't be out of the, this is out of range index, right? Okay, so now let's take a look at the first one. Check this out. Okay, so let's take a look. Now, which tree size is this? Which tree size is it? Well, is it the receiver? Because it's tree arrow data arrow size. And what is tree? Tree that's the parameter. Are you with me? So which tree size is this? That's the tree size of this one on the right. Okay, so anyway, so now, if tree size equals 0, so that's a special case, the tree being inserted is 0, then we just return, all right? And then there's another special case for the receiver tree being empty, and if the receiver tree is empty, then we have that, if the receiver tree is empty, and so that's underscore data arrow size equals 0, then we have this special case where we just insert the receiver tree into the, we insert the tree to be, we insert the right-hand side into the receiver tree. But now look, This line of code that's indicated here is underlined, corresponds to part B of that sequence. Remove I from your tree, replace the right child of 90 in my tree with it. Now let's parse through this code. What is it doing? It's doing star underscore children sub I, so that is the receiver tree at position I, and what is it getting?
The furthest most data thing.
Yes, the farthest child on the right of the tree that's being spliced into it. Are you with me?
And then it shrinks the size of the tree
And then it shrinks the size because it's minus minus by 1.
in that order. Right, it gets.
Yes. It gets the sub-tree size, and then it decreases tree size by 1. And it's the children of the tree. Yeah. Are we good? Is everybody clear on this?
We're trying to understand if tree size is the length of the vector, then how can you remove that length? How does that impact?
Oh, because it's sub. This is, it would be this one. So did we get it? Are we clear? All right. And now, you guys, I set up the loop for you. For int k gets for int k gets tree size, k greater than or equal to 0, k minus minus. So this is an exercise for the student. You know how we did those in pairs? So you have 2 lines of code to write here. One for the data and one for the child. Yeah, I think you can handle that. I see some heads nodding. Are we good? Okay, so this is how you remove 90 and H from your tree and insert them after 90 in my tree, but then you do it and then that happens in a loop. All right? Okay, now, next one is mytree.splitDown@2. Now, before we go on to mytree.splitDown@2, what do we have to do? Let's imagine what this does. Split down at. So what is underscore data sub 2? Which one is that?
10.
I don't think so.
60.
I think it's 60. Isn't it?
No, you're right.
It's the 60, yeah?
Okay.
So what's going to happen is 60 is going to do what? 60 is going to come down, and what's going to come down with the 60?
70 and 10.
No. 70 and 10 and the 90, no. Only one element is going to come down. We're going to split that one down. Remember from the demo last time? Just the 60 is going to come. But then now what's going to come down with it?
CD.
The C and the D, I think, right? And then what's going to happen? The new one up, the new node is going to be what? Yeah, be 70, 10, and then that's going to be what? Joined with the what? The 90 and the 40 and the 20, right? Does everybody remember how that worked? Okay, from the demo? Here, let's go to the last one and see. See, it's going to be like this. That's what it's going to end up. Are you with me? Okay, so here's how this operation works. Okay, so first of all, because we're going to have a new tree, right? So what we have to do is we have to create a new single tree with 60 removed from my tree and the same left and right children. Ooh, it looks like a job for our old friend, the constructor, right? That we just looked at. Huh? Okay, so we create a new single tree with 60 removed from my tree and the same left and right children. So C and D, the same left and right children. All right. And then what we're going to do is we are going to remove the old left child of 60. Remove the old left child of 60. Now, who's the old left child of 60 was what? No, at the beginning in part A. That's what I meant. It's C. Are you with me? It's C. Now, Okay, so now, look, because you look, you see, in part B of the figure, it is, we still had A, B, C, D, E, F, G, but what happened was when we removed the data part, we still have what? When we removed the data part to make that new tree, we still had those A, B, C, D, E, F, G up for the children. Are you with me? So how do we remove that? So do you see when we remove that? But that's a vector. So when you remove from a vector, what does it do automatically? When you remove from a vector, what does it do automatically? Shifts to the what? Shifts to the left. So we're going to remove that, and those children, so the D, E, F, and G are going to get shifted over. So that's how you remove the old left child of 60. Are you with me? See how neat these vectors are? Okay. And then what we do is we set the old left child of 60 to the new single tree. Now, by the old left child of 60, I mean the one between 10 and 90. Are you with me? And that's it. Okay, so now let's take a look at the code. So here's the split down at. All right, so now here, and we have some special case. Now, this underscore data arrow size, that's our original tree, right? So if it's 0, that's a special case. We do nothing, that we return. That's part of the specification for split down at. And then here, in that case, we don't care about the indexes being out of bounds. Okay, so if we don't do that special case, then we implement the precondition for the. And this here again, this is just I, the position being not less than 0 and not bigger than the size. Okay, so that's the usual precondition. Okay, so now let's take a look here. If underscore data arrow size equals 1. Now, do you remember? You might not remember this, but because this was before Thanksgiving. But there was a special case when we looked at the specification for split down at. Do you remember we said that if there's just one, like if this is 70, and and if you do a split down at 0, that this just goes away. That's a special case. That's kind of a weird special case, but we need it for our future. We will need this behavior in the future. So if underscore data arrow size equals 1, and then so this goes away if we do a split down at 1. If we split this one down, and so we do underscore data arrow remove 0. So data is now empty, and then we delete children, and we delete children arrow remove 0, and then we delete children arrow remove 0. So the first one deletes this one, and this one shifts over, and then it deletes this one, and then that one's gone. And now, you guys, here's your job. Well, not yet. So this line creates a new single tree with 60 removed from my tree and the same left and right children. So this is NTree T star new child gets new, and now what do we have? NTree get child sub I, underscore data remove sub I, get child I plus 1. Now, are we clear about this one? This is calling that constructor. Are you with me? With those pre-existing trees. Are you with me? And we're giving underscore data arrow remove sub I. Yeah, is this pretty clever? All in one line with that nifty constructor. So this is doing part B here. This is doing, let's go back to the figure. That's doing this part B of the figure. Okay? And now what do we have to do? Remove the old left child of 60. So now we have to remove the old left child of 60, so that's your job. Exercise for the student. Remove the old left child of 60, and D, set the old left child of 60 to the new single tree. All right, so I think you can See how to do that, I hope. And now the last one is the hardest one. The split up. This is a little lengthy. So now, if we do mytree.split up at 2, now what happens? Now instead of the 60 going down and we joining, what happens? The 60 goes what? 60 goes up, and then it has what? What is the left child of 60? 70, 10, and the right child of 60 is what? 90, 40, and 20. Are you with me? And the children are all fine, right? I mean, we don't have any like leftover children or anything like that, right? All right, so here we go. First thing we do is we allocate new data and children vectors, because see, we're going to have a new tree here. We allocate new data and children vectors, and we remove and save the 60. So the new data and children vectors are indicated by that empty tree, okay, on the left there. And now what we have to do is in a loop. Now here again we do it in pairs. We do what? We remove 70 in A and do what? Append it to that new empty one. Are you with me? And then in a loop do what? Yeah, so the next one would be what? The 10 and the B. So in a loop, you see, you take the 10 and the B and whoosh, put those in, right? 2 statements, one for the data, one for the vector, all right? And now what has happened is we still have this G over here, right? One too long, right? So here what we do is we remove C. So once we remove C, then that G gets shifted over and we append that to the new children. Are you with me there? And then we make a new tree for left with new data and new children, and a new tree for right with the current data and the current children. All right? So left becomes the 70 and the 10, and the right becomes the 90 and the 40 and the 20. And then what do? We allocate a new vector for underscore data, and we append 60, and we allocate a new vector for underscore children, and we append left and then right. Yeah.
Do we need to explicitly make a new tree for the right, or is that already a tree?
That's a good question. Let's go to the beginning. In the beginning we have what? How many trees do we have in the beginning? 1. How many trees do we have at the end? 3. Are you with me? So we're going to have to allocate 2 new trees for this to work. And those 2 trees get allocated where? Well, actually it's... that's a good question. Let's do a code walkthrough and remember step F. Okay, so here's our split up. And here's our code walkthrough for split up. And let's remember step F. All right. So here's a special case. If data arrow size is less than or equal to 1, we return. So now if you split up and there's only one element, nothing happens. All right? So that's a special case. And then here's I did our precondition. And here in step B is allocate new data and children vectors, remove and save 0. Now notice that this involves what? New. Because remember in step B, that was that new, are you with me? That was that new tree got allocated. So this was allocate new data and children vectors, remove and save 60. You know what? It's getting, let's zip through this and then we'll come back and we'll do it again tomorrow at the beginning of class. And so, and this is one exercise for the student on this is in part C. This is the code that happened in part C. In a loop, remove 70 in A and append the new data and new children. And in a loop, remove 10 in B and append to new data and new children. So that's steps C and D. And then here in E is where we remove C and append the new children. And here, to answer your question, is what happens in F. Make a new tree for left with new data and new children, and a new tree for right with current data and current children. In part B, we are not allocating a new tree, we're allocating new vectors. Are you with me? So in part B, we're allocating new vectors. In part F is where we allocate the 2 new trees. Oh, that was a really good question. I stand corrected. All right, so anyway, we'll take a look at this. I think for your homework for next time is to do this, right? So we'll do some more. We'll take up here, and we'll look at this in a little more detail next time. All right, good deal. Nice to have a visitor. See you tomorrow.